Carlino, are you there? We're not hearing you.
Yeah, I can hear you. Hi.
Okay, so I'm gonna start then introducing you, and if you're ready.
Yes.
So, hello everyone. It's a pleasure to introduce today Carlos López and Juan. He got his PhD in 2009 at the ISC in Spain, studying galaxy mergers at cosmological distance. First postdoc at the LAM in France, he moved to the Centro de Estudios de Física del Cosmos de Aragón, CEFCA, in Teruel, Spain, in 2012. Since then, he has been developing statistical tools for multi-filter surveys such as J-PLUS and J-PLUS to study galaxies and Milky Way stars. He is the head of research area in CEFCA since 2020 and deputy director since 2023. Thank you so much, Carlinhos, for accepting our invitation. Before we start, we would like to remind everyone, especially the students, that you can scan this QR code here to write down your questions for Carlinhos at the end of the talk. It can be in an anonymous form, or if you would like to spell out your name, you're very welcome to. So, Carlinhos, the floor is yours when you're ready.
Okay, thank you. Thank you very much, Anna, for the invitation to give this talk. I hope that you are hearing me well. If there is any problem in any moment, just let me know, and we can resume when the problem is solved. So today I'm going to make a seminar about the spectral evolution of white dwarf in J-PLUS. This is a work that we published 2 years ago in Astronomy and Astrophysics. And you can see some of the collaborators, Pierre Tremblay, Alessandro Redoclite, and many others that with work or ideas were present in this work. So let's start from the beginning with an introduction to white dwarfs. So I like to show you this the first Hertzsprung-Russell diagram that was published. You can see in the figure in the x-axis you have the color of stars, and in the y-axis the luminosity, or the brightness that these stars are. So this first HR diagram was constructed with more or less 100 stars, for which parallaxes, that means distance, that means luminosities, were measured at the 1 century ago. So what Russell in the US and Hertzsprung in Europe discovered is that basically most of the stars are set in the diagonal. There are 2 lines there showing what we call now the main sequence, and that in the case of the red objects, there were dwarfs, low luminosity objects, and giants, high luminosity objects. And that was basically the discussion in the paper. Interestingly, there was also a blue object that was a dwarf in the dwarf luminosity region. So I marked it here in blue just to highlight the position. And in the original paper of Russell, basically they discuss this object. This is in a 40 Eridani B. So B means that it's a companion of 40 Eridani, because the luminosity of this object was very low and the 40 Eridani A was very bright. In the discussion, they say that, well, probably this is a mistake. So we put in the diagram, but probably in the future, we will solve the problem with this measurement. So that was not the case, because later, 1 year later, Sirius B, that you can see in a beautiful image for the HST, in which Sirius A is very, very bright, and then there is a small fine dot, which is Sirius B. was also placed in that corner of the HR diagram. And 5 years later, Van Manen star was also placed there. Van Manen star was important because it was an isolated object. So no issues about the bright component. So when we have 3 objects in the same place, probably it's not a mistake and it's a new population. So even in this moment, at the beginning of the 20s, in the past century, there was a discussion about if these objects can be real or not, because thanks to the location of Sirius B in a binary system, we measure the mass, that is basically one solar mass, and from the luminosity and the temperature, we can derive the radius. And the conclusion is that we have some mass object with the size of the Earth. It's what people start to call a white dwarf because of the luminosity, and white because they were blue objects with some extreme densities. Now, 1 century later, these are not extreme objects. We have neutron stars, we have black holes, but at that moment were the densest objects in the universe. And there were doubts about if the matter can stay in such a dense state. So in 1924, there was a theoretical prediction from Eddington using the general relativity equations. And Eddington predict that if Sirius B is as dense as we are assuming, then the light has to be affected by the gravitational potential, and the spectra have to be redshifted. So 1 year later, Adams indeed measured this gravitational redshift, so it was great news because that demonstrates that white dwarfs as dense objects in the universe exist, and also is one of the 3 classical proofs of the general relativity, also together with the famous eclipse experiment and also the Mercury precession orbit. But how we can make the matter to be stable? Luckily, just 1 year later, in 1926, Fowler provides that electron degeneracy pressure that was like that was just a quantum analysis can provide enough force to avoid the gravitational collapse. So we have already something that is very dense. We observe that, and we have a way to sustain that high density mass. Just as a curiosity, the way that the sun and other main sequence stars emit the collapse, so nuclear reactions, was settled in the 60s, so 40 years later. So we discovered white dwarfs in 1915, and 10 years later, we know more about them theoretically than from stars. That was very impressive. So, but the thing is that by 1930, white dwarfs were a consolidated astrophysical object, and in astrophysics, when we have an object, what we want now is a population. So we want more and more to study their physical properties and to understand the physics of the population. So in the last century, there were 2 main ways to look for white dwarfs. Here you can see 4 images taken at different epochs from 1989 to 2017. And I don't know if you can see it, my mouse, but there is a small dot marking the position of this white dwarf in the latest epoch. And if you go to previous epochs, you see how it moves, something that doesn't happen with the other 2 objects that you can see in the field. So looking for high proper motion stars was a very efficient way to discover new white dwarfs. Why? Because they are low luminosity objects. So at a given observed magnitude, white dwarfs are the closest objects that you can see, and those are those that move faster. So looking for high proper motion provides you candidates to then follow up with spectroscopy and confirm them as white dwarfs. The other way that we use it was, for example, looking for bright objects in ultraviolet, because they are hot objects, so they are very bright in ultraviolet. So you can go to galaxies or to U band selected objects in the optical. You're going to have a lot of quasars also, but you're going to discover many white dwarfs. But you can think, okay, this is not very clever, because we saw at the beginning, the luminosity of a white dwarf is like 10 magnitudes less than a main sequence star. So you only need to go to the HR diagram and look for objects in the region of the white dwarfs. However, for that you need distances, so you need parallaxes, and measure parallaxes is very difficult, in the sense that if you think about the closest star to the Earth, that is Proxima Centauri, is basically 4 light years. And that means that the parallax of this object is less than 1 arcsecond. And 1 arcsecond is the, let's say, typical scene, typical resolution that you can have from Earth due to the atmosphere. So basically, only the very bright objects can have parallaxes. And if you want really to make measure of parallaxes of distant objects, you need to go to the space. So this is why the next step in parallaxes measurements and the next step in the construction of HR diagrams were in the 90s of the past century, when the Parco satellite was launched. Even in that case, only 300 white dwarfs with parallaxes were available. That was the state of the art at the beginning of this century, and then Sloan Digital Sky Survey started and took a lot of spectra of UV bright objects. So at the end, we have like 300 white dwarfs with parallaxes, but we gather like 30,000 spectra of white dwarfs. So 2 orders of magnitude more spectra of white dwarfs than parallaxes. However, things turn around when Gaia was launched, and in 2018, Gaia released 1 billion parallaxes, high quality, and suddenly we populated all the white dwarf region in the HR diagram. So we go from 300 to 200,000 candidates of white dwarfs, for which now there are massive campaigns of spectroscopy in WINF, Formos, SLOAN 5, and DESI to observe most of the white dwarfs in the Gaia catalog, to have a spectra of them. Okay, so now we have a rich data set to analyze. So what we can do, if you go to the latest version of the Gaia catalog, that is the Gentile Fusiro 2021 based on Gaia DR3, you can see in the figure, again, the HR diagram, but in this case, the absolute, in the x-axis is the Gaia color, and in the y-axis is the absolute Gaia magnitude. In blue, you see all these candidates for white dwarfs. So we have these candidates, and also thanks to the Gaia 3 magnitudes that Gaia provides, we can compute the effective temperature of the white dwarfs and also the surface gravity. In the right panels, you can see in the upper one a comparison between the effective temperature derived from the Gaia photometry with respect to effective temperature derived from spectroscopy, and you can see a very nice agreement, almost 1-to-1, and the same in the lower panel for log G, for the gravity. So let's say that for temperature with 1 color is enough. Okay, you measure the color and you have a good idea of the temperature. But for the gravity, it's not evident that you can measure only with photometry, because the information of the gravity is in the absorption lines, in the width of the absorption lines. The wider the absorption lines in the spectra of the white dwarf, the higher the gravity. And of course, with the with the colors, you don't have enough resolution. So how you can derive the gravity? Well, white dwarfs are, let's say, simple objects, at least when we compare with other astrophysical objects there. So just knowing the temperature and the gravity, we can model the luminosity. So with the temperature and the gravity, we know the luminosity. And then when we compare with the observed magnitude, we can measure the distance. That was what people did with the spectrum in the past. But now we can turn around the problem. We know the apparent magnitude, the magnitude that we observe. Thanks to Gaia, we know the distance, so we know the luminosity of the white dwarf, and we can measure the temperature. So the only from this, we can derive a very accurate surface gravity. So now we have all what we need to study white dwarfs. Well, there is one key missing component, that is the atmospheric composition. Not all the white dwarfs are the same. Here, I'm going to present you what is the taxonomy that we use in the white dwarf community. I started with what is called DA. In the DAs, what you observe, as you can see in this Sloan spectra of a DA white dwarf, is the Balmer series in absorption. So basically, there are objects in which the atmosphere is dominated by hydrogen. And this is why you see all the Balmer lines. We also have what is called DBs. I mean, DBs are those in which we see helium lines, so are helium-dominated atmospheres. So the lines that we see are of helium. If helium-1 is called DB, if you are in a very hot system, you don't see the helium-1, but you see the helium-2 absorption line, and it's called DO. So DOs have temperatures above 4,000 Kelvin, and DBs above 11,000 Kelvin, more or less. When we go below this temperature, we depopulate the ionization states, and basically the lines disappear. So it's what we call DCs. Cs from continuum. We see no absorption line is basically a continuum spectra. So this happened for helium-dominated atmospheres below 11,000 Kelvin, and also for DAs, let's say for hydrogen-dominated below 5,000 Kelvin. But there is more things there. You can find, for example, metal-polluted systems, what we call these sets. Set is for the metals. Here you see an example of something of a white dwarf that basically has no absorption, but the calcium H and K line. This was very weird at the beginning when these objects were discovered. I was a discussion about what is the origin. In principle, because of the high density and high gravity of white dwarfs, all the heavy metals goes very fast to the center. So you end with a stratified white dwarf. So you don't expect to see metals in the atmosphere unless they have been accreted very recently. So now this is the interpretation that we use for these systems. There are white dwarfs that have accreted recently material from exoplanets, from exomoons, from exocomets in the ancient planetary system of the white dwarf. Also, you have some with carbon lines, the DQs. In this case, the carbon is not from outside, but you usually have in the core, you have carbon and oxygen. And when the temperature goes down, you can have some convection zones. So you can reach up carbon from the center of the white dwarf to the upper part. And in this case, it's a cool DQ in which the lines are molecular swan bands, so it's very, very impressive to see all these wiggles in the spectrum. Also, you can have magnetic variable objects, peculiar objects, and that's only talking about the individual objects. Then you can have binaries. You can have double degenerates, in which you have two white dwarfs in the system. You can have a white dwarf plus a red dwarf, like in the example that you can see. So in the blue, you see a DA with the Balmer lines, but when you go to the red part, you start to see the typical absorption features of red dwarf. Also, if this red dwarf is very close to the white dwarf, you can have accretion, and is when you have cataclysmic variables, for example. This is an example in which you have an accretion disk, so you can see H alpha and H beta and other Balmer series in emission. So, as you see, a great soup. But what happens if we take two big families, let's say DAs, that are the most common white dwarfs in the sky, and non-white dwarfs, other objects. So this is what you can see here in the fraction of non-DAs over the total number of white dwarfs as a function of the effective temperature. Think that white dwarfs only can, when they form, they don't have nuclear reactions in the interior, so they only can cool down. This is why we have lower temperatures on the right. That means older systems. This is why in all the plots that you are going to see, temperature decreases to the right. That means that time, the cooling time of the white dwarf, is increasing to the right. So when we make this plot, and this is plot for the late 80s in the past century, we found that non-DAs are basically 100% at the very beginning of the white dwarfs. Then as they cooling down, basically we go to only DAs. This is because at the beginning there is very turbulent atmosphere, but as time goes by, the heaviest elements go to the center, and we end with this stratification. So because hydrogen is very sparse in this object, you need them to be stratified to have a helium-dominated atmosphere. Because in the moment that you mix the hydrogen with the helium is much more abundant, so you observe a helium-dominated atmosphere. So let's say that the hot part is explained with this stratification. You go from mixed atmospheres to stratified ones in which the hydrogen is dominating. And then when you arrive to lower temperatures, the non-DA fraction increases again. In this case, what the physical interpretation is that you start to have convection zones that are able to mix the hydrogen and the helium. As I told you, helium is much more abundant. So in the moment that you have some convection and some mixing, you change the atmosphere for DA to DB or DC in the case that the temperature is low. So what is the status of this? This is what we call a spectral evolution, and is what we want to study. Here you can see more or less what is the status like 5 years ago, in which you have a lot of data at temperatures higher than 20,000 Kelvin. There is like a minimum fraction here at the level of 5–10%, and then an increase. But as you can see, there is a lot of scatter. So the thing is, how we can improve this? This is where the data from J-PLUS in the observatory enters. So I'm going to give you some introduction to the Observatorio Astrofísico de Javalambre. This is a map of Europe of the light pollution, and we are here in Teruel. We are in the darkest spot. We are in one of the more underpopulated regions in Europe, and because of that, we have very dark skies. Also, we have high mountains, so and in one of them, we have competitive scene. So 1 decade ago, we constructed a new observatory, the Observatorio Astrofísico de Javalambre. You see here the photograph. We have different buildings. We have some sky monitors, a scene tower, a main dome in which we have a 2.5-meter telescope that is devoted to the J-PLUS project. I will tell you about it later. And we have a small dome with an 80-centimeter telescope that is devoted to this J-PLUS. So if we go inside the dome, we see that the HAST 80 is an 80-centimeter telescope with a large field of view and a very good quality about all the field of view. And it's mounted with 80 cam. It's a one detector, 9K by 9K, with a 0.55 arcseconds per pixel scale and a field of view of 2 square degrees. So just an example, this is just one image of TAT is 1.4 by 1.4 square degrees. And the galaxy that you see here is M101. M101 usually is very big galaxy for other instruments, and you need several pointings to cover all the galaxy. But for us, it's like a small object in the field. So with this camera, we were performing the Havalambre Photometric Local Universe Survey, J-PLUS, and we are using for this work the second data release that was made public in November 2020 with roughly 2,000 square degrees of the sky covered. It's not only the area, 2,000 square degrees, but also the filter system. So J-PLUS is observing with 12 filters. We have the 5 slow ones, U, G, R, I, and Z. They are broadband filters that are covering the full optical. But in addition, we have 7 narrowband or medium band filters located in key spectral features like the oxygen 2, the magnesium, H alpha, the calcium triplet. So this is well suited for make physics of Milky Way objects and nearby galaxies. So these are the data that we have. And so the goal of the work is to take the Gaia DR3 catalog of white dwarfs and complement it with the 12 optical bands of J-PLUS in 2,000 square degrees to derive the atmospheric parameters and the composition of those common white dwarfs, and with this study the spectral evolution with effective temperature. So the first thing is how we derive these atmospheric parameters and the composition. Well, here's an example of a white dwarf observed by J-PLUS. You can see the 12 points covering the optical. And what we did is to perform a fitting to obtain the probability distribution function, the PDFs of the composition, this T, that can be helium or hydrogen, let's say helium dominated or hydrogen dominated. And also we derive the parameters of interest, that in this case was the effective temperature, the surface gravity, and the parallax. As I told you before, log G and parallax are very connected. So if you know one, you know the other. And one thing that we do is to complement the likelihood from the data with some priors. And in this case, we use the Gaia parallax as prior. So thanks to the Gaia parallax that is very precise for this sample, we have a good measurement of log G. Thanks to the colors of J-PLUS, we have a good temperature. And also, thanks to the different narrow bands, we can also discriminate between DAs and DBs. So in this case, you see the fitting provides some measurements and also the probability of being hydrogen dominated, and this in this case is 1. So this will be cataloged as a DA. So regarding the models, we use pure hydrogen models for DAs and mixed models for non-DAs in this case. So we run this in all the common sources, and this is the catalog that we obtain. So at the end, we have roughly 6,000 white dwarfs in common with the Gentile Fusillo 21 catalog, selected with a magnitude of 90.5, so we have good signal to noise, and with a parallax between 1 and 100, so we have good parallax measurements. So in the figure, you see the number counts. This is the number of white dwarfs of a given magnitude per square degree and magnitude, and you see that we have the typical exponential increase from magnitude 13 to magnitude 19.5, that is our selection limit. And basically, we have like 3 white dwarfs per square degree. So as you see, they are a sparse object, only 3 in 1 square degree. This is why large area surveys are very important to study white dwarfs. And this is why J-PLUS, when you combine Gaia, that is all sky, with J-PLUS, in this case, we can have large samples to study white dwarf populations. So one of the first things that we did is to compare the effective temperatures from J-PLUS with those from the Gaia colors. Here you can see the one-to-one comparison, and basically the red points are the individual measurements, and the white points are the median in different temperature range. So we find that almost perfect one-to-one relation, only a 0.6% difference. The good thing is that with J+ we have more bands than in Gaia, in this Gentile Fusillo catalog, so our errors in the effective temperature are a factor of 10 lower than in the Gaia catalog. Also, the same for the gravity. Again, we find a very nice agreement, but that was not surprising because in both cases the gravity is dictated basically by the parallax information, and we are using the same parallax, so it's nothing impressive here. And finally, the most important thing for this work is that the J+ filter system permits to classify the white dwarfs into helium and hydrogen dominated. Here you see two examples of two white dwarfs of similar effective temperatures, 16,000 Kelvin, but different compositions. And you can see how the photometry is different. So we can from J+ we can say that the upper object is hydrogen dominated and the lower is helium dominated. So now we have everything that we want. So we make a final selection just to take objects with masses higher than 0.45 solar masses, just because objects with lower masses are probably binaries, and we don't want binaries in our study. And we also keep us between 5 and 30,000 Kelvin because it's where the temperature and the selection makes sense. So what are the results that we found? We found an increase in the fraction of helium white dwarfs below 20,000 Kelvin, but this can be a physical results, but also can be a biased result, because as we go to lower temperatures, as we go to the right, the lines are less and less prominent, so it's more and more difficult to disentangle between the both types of white dwarfs. So basically, in a natural way, we are going to tend to a 0.5 fraction at lower temperatures. So that can be just an observational bias due to the fact that data have its own limitations. So let me illustrate this in the way of measure this fraction. If you remember, we put a prior in the parallax, but we didn't put any prior in the fraction of helium white dwarfs. And from this figure and from previous results, we know that the fraction of helium white dwarfs is not 0.5, so a 0.5 prior is not a good choice. For example, we can use, and as an example, a prior of 0.2. So what happens if we repeat all our analysis using a prior of 0.2 in the fraction of helium white dwarfs? We obtain the red points. So the interesting thing here is to see that at lower temperatures, the prior is changing dramatically the results, while above 10,000 Kelvin, the change is subtle. So that means that J+ information is prominent above 10,000 Kelvin, but when we go below that temperature, we start to be in the noisy part, and then the prior start to dominate. So how we can solve this? We can take previous results and make an empirical prior for this fraction, but this is what we want to measure. So it's like some circular thing that we don't want to do. So how we can solve this problem? For that, we did what is called a hierarchical Bayesian model, in which instead to assume a prior, what we assume is a functional form for the prior. And the parameters of that functional form are fitted with the data. In other words, basically, we derive the most consistent prior with our data. So here, this is an example of what we assume. We assume a linear function that can increase or decrease, this is free, with a minimum fraction of white dwarfs, of helium white dwarfs in the higher temperature. That again is free, can be 0 or can be larger than 0. And what we did is just to test different priors, let's say different red lines, and we compare with the posteriors, with the red dots. So the good prior, the best solution, the self-consistent solution is when the red input line is most similar to the red output dots. So we do this with a Monte Carlo Markov chain, and this is the final result that we obtain. Basically, we found like a 8% fraction, lower fraction, minimum fraction of helium white dwarfs at higher temperature. And when we arrive to 20,000 Kelvin, it goes up. And you can see how this Bayesian model is affecting the low temperature points. So this is our final result. So now it's time to compare with the literature. These are results from Tremblay, 2008, very large errors, but as you can see, we are more or less in the same values. These are results from 3 different works that are based in spectroscopic classification. So remember that we use photometry, they use spectroscopy. And the most interesting thing is that we found a consistent result in the high temperature end, and then something that resembles the increase that we found. At lower temperatures, there are large errors, but we are compatible basically at 2 sigma with the results. Also, this is a very interesting comparison. This is for Ulrich, 2019. This is based on Sloan Digital Sky Survey spectra. So again, a spectroscopic classification. And we know that Sloan spectra are complete or have no selection bias at higher temperature, let's say for blue objects. But when you go to red objects, they started to pre-select the targets. So you have selection effects. This is clearly see here. Between 30,000 and 15,000 Kelvin, we have basically a perfect match. And then below that temperature, things start to go wild. This is probably because of the selection of Sloan, and in this case, our results are probably okay. And finally, this comparison with Cunningham that is based in some ultraviolet optical classification. We obtain a very nice agreement till their lower temperatures. Probably they are having the same issue that we had when we don't apply this hierarchical Bayesian model. And also McCleary, that is a spectroscopic survey, we also have compatible results. So very nice agreement with the literature. One thing to say is that we published our work in 2022, but in the meanwhile, Gaia DR3 appeared, was released, and Gaia DR3 had low resolution spectra. So this work has been already done with the low resolution spectra from Gaia. And this is the comparison. This is a recent work from Torres, 2023, using this Gaia BPRP low resolution spectra for the classification. And again, we found a very nice agreement almost till the end. Again, probably the issues, the higher values that they have at the lower temperatures can be explained with the problems that you start to have with the data at lower temperatures, because again, they didn't use a hierarchical Bayesian model to take into account these effects. So great. This is what we obtained, but something that we did later is to test if our probabilities, if our classification is good. So basically, what we did is to cross-match our J-PLUS Gaia catalog with the spectroscopy in the same area. So we found like 900 DAs and 300 non-DAs with the spectral classification. And in the figure, you can see the normalized histogram as a function of the probability of being hydrogen dominated. So for DA, you have a very nice peak at 1, is what you want. And then for non-DAs, you have a very clear peak at 0, again, is what you want. Of course, we can start to discuss about purity, about completeness, but this is not what we are interested on at the end. What we want is our probabilities to be representative, and how we can test this. So in this figure, in the x-axis, you see the probability of being hydrogen dominated atmosphere, and in the y-axis is the fraction of all the objects with with a probability pH that are indeed a DA from Spectral. So let's point this way. If you have 100 objects with a pH of 0.5 and then you make a spectra, if your probabilities are good, are reliable, then half of the objects are going to be DAs, so hydrogen dominated, and half of the objects are going to be non-DAs. That doesn't mean that the classification is wrong, because the pH already tells you that half of the sources are not going to be DAs. So what you want when you create this figure is to be in the diagonal, in the dashed line. So that provides good calibrated probabilities. So if we compute this without the prior, the self-consistent prior, we obtain the black points that you can see here. So we are far from the diagonal. But when we apply the self-consistent prior, we go to the diagonal. We are compatible with a well-calibrated probability. So remember that we only use our own data to go for the black points to the red points. So no spectra were used in the process. The spectra only used for testing. So this is a very nice result and supports that we are doing properly the statistical analysis of the data. So now that the probabilities are well measured, it's nice because we can, for example, use this to make selections. We can go to objects with probability higher than 95% and make a spectroscopic follow-up. But also we can study the distribution of the properties, not by selecting, but not selecting different objects, but weighting the objects by their probability. This is what we did here again to test our classifications. This is the mass distribution for the objects that we have closer than 100 parsec, with a temperature higher than 600 Kelvin, and again with a mass higher than 0.45. So what we found when we make this histogram that of the mass that is weighted with the probability of being hydrogen dominated, so all the sources are here. If your probability is 0.5, it's going to count as 0.5 sources in the histogram. This is fair because the probabilities are well calibrated. So what we found is a peak at 0.6, and then let's say an excess or a second population basically at 0.8. This high mass excess was already observed, and here you can see the results as a black line from Kilich 2020, in which the classification was based on spectroscopy, but the mass was based on photometry. Here the black line is not a fit to the J-PLUS data, it's just the result from Kilich with exactly the same selection. This is why we provide this selection. And we obtain basically the same results, again, with our photometric classification. Now we can go to the helium dominated, and what we found is that there is basically a main peak at 0.6, more or less, but that the excess and 0.8 is not present in helium dominated. This is more clearly seen if we compute the cumulative distributions. So the cumulative distributions are the colored lines, and the areas depict the 3 sigma confidence intervals from this. So we found that helium dominated and hydrogen dominated have different distributions in mass at 3 sigma level. This was also provided in the literature, and again, that provide us more confident in all our results about the spectral evolution, because our classification is providing meaningful results in all the tests that we perform. Finally, this is what we did with J-PLUS, but the future for us is J-PASS. J-PASS is the Haber-Hambre Physics of the Accelerating Universe Astrophysical Survey, in which basically we want also to observe a large area of the sky, thousands of square degrees, but not with 12 filters, but with 54 filters of 14 nanometers. You can see here all these small filters. They are separated by 100 angstroms, so you have a continuous coverage of the optical spectra, providing a resolution between 40 and 90. This is complemented with 2 broadbands, one in the blue and one in the red. So we have two extra points, and also an additional detection band that is the I band, that is much deeper, just to perform the detection and the force photometry. So this is similar to the Gaia DR3 spectral that I explained to you previously, that they have also a 3090 resolution. So it's very interesting because we have two different data sets, one from low resolution spectra, one from high resolution photometry, let's say, that can be complemented and compared. So we started 1 year ago, the J-PLUS in the OIG. We have 30 square degrees that were released like 1 week ago to the collaboration, but in the meanwhile, we were able to observe 1 square degree with all the J-PLUS filters to nominal depth. Is what we call it mini J-PLUS because it's like a small version. Is 4 pointings of the camera in a strip, as you can see in the figure. And you also can see an example of the Milky Way star, a quasar, and a galaxy in the field. So these data were made public in 2019, and we also analyzed the white dwarf population. Of course, white dwarfs, as I told you, are very sparse, and we had only 11 white dwarfs in this field. But well, that was enough to have an idea of how things can be improved. So this is a white dwarf observed with J-PLUS, and this is the J-PLUS counterpart. It's the same source. Very nice how we can recover the Balmer lines, H alpha, H beta, H delta, H gamma. So these bump here in the blue lines are real. We know that are real because when we overplot the Sloan spectra of this source that is available, we see how all these absorption lines are very nicely recovered. So we already performed the same set fitting analysis with this. So in this case, we obtain a much more precise temperature, 2% error. And of course, we have also a very nice classification, much nicer than with J-PLUS because we have more data. So indeed, when we make some analysis about what are the limits, in J-PLUS we started to have problems at 9,000 Kelvin, but here you can see an example of two white dwarfs of 7,000 Kelvin, and it's no doubt that the upper one is a helium dominated, a DA. We see subtle, but is there the H alpha, H beta, and also the higher opacity of the atmosphere in the ultraviolet bands. While in the lower case, we have like in this case, a DC, because we have below 11,000 Kelvin. So basically, the shape is featureless. So the current J-PLUS CDR is 30 square degrees, so we expect like 300 white dwarfs. So now we are starting the analysis of this population. Let's see what happened. And I'm going to stop here. These are my summary. So in J-PLUS, we were able to measure the effective temperatures of white dwarfs with a 5% uncertainty and have a reliable probability for the classification into DAs and non-DAs. So the fraction of helium-dominated white dwarfs increased by 20%, basically, from 20,000 Kelvin to 5,000 Kelvin, with a minimum helium-dominated fraction of 8%. And we expect in the future to improve this analysis with J-PLUS data. So this is all. Thank you very much for your attention, and I'm happy to take your questions.
Thank you, Karina. Do you have questions from the audience? Ale and the students? Did you write down your questions here? You want to write them down? Okay, go ahead. Okay. Hi, Carlos.
Hi.
Hear me?
Yeah, I can hear you with some noise, but let's see if I can get your...
Closer to the microphone, don't worry.
Yeah, please.
There, okay. Okay, so can you go back to the slide that you compare with the Aurique 19 paper?
Yep.
Okay, just to clarify, that drop at 10,000, that is real.
Okay. Yeah,
It has to do with a parameter that I don't think that is being considered. That is the amount of hydrogen that you have. Because not all white dwarfs have the same amount of hydrogen or helium, okay?
Yeah.
And you actually have two drops because they mix at different temperatures. Once the convective region gets to the bottom of the hydrogen layer, then you get the mixing with the helium. So if the hydrogen layer is thinner, you will get to mix at higher temperatures. And that drop is for the ones that have a thicker hydrogen envelope.
Okay. Yeah, it's indeed, if you see in our data in the J-PLUS, we also have that drop.
Yeah, you also have the drop. That's why it's not noise, it's not bias, it's there. So if you can detect it with your data, then just to clarify, it's there.
Yeah, in this, more than the features is that they have like this offset with respect to our results, and this is why that can be due to the selection function of the Sloan. This is one of the possibilities. But yeah, at the end, this feature can be real. Yeah, but
that goes to my second comment. That offset can also come from the models that you're using. I noticed you're probably using Pierre-Emmanuel Tremblay's atmosphere models.
Yeah.
Right. And the thing with the hydrogen and the helium is that you can still have a little hydrogen, but you don't see it. But that hydrogen will change the pressure, the atmosphere pressure, and that would will change a little the log G and thus the fit.
Okay. Okay.
So,
yeah. Indeed, one of the things that I can tell you that when we did this work for the first time, we used pure helium models for, let's say, helium dominated, and basically we obtained the same results. The only thing that changed was the peak in the mass. So the peak in the mass distribution for helium dominated just moved, but the colors and all the other results that I present to you in this presentation were not sensitive to the use of mixed or pure helium models, because basically the colors were very similar, just changing the mass distribution, let's say how the mass between colors and mass are mapped. Yeah.
Can I just mention one little thing?
Yeah.
Okay. Last one, I promise.
Is there any questions from Zoom or YouTube while Alejandra finishes her question?
Okay, thank you. The thing with the log G and the mass, okay? To go from log G to mass, you need a radius.
Yeah.
And Manuel uses Gilles-Fontaine models.
Yeah.
And Gilles-Fontaine models have the same amount of hydrogen for all the masses, which is not true.
Okay.
So you will have, when you go to mass, you need to be careful with that.
Okay.
Because the helium or the hydrogen in mass is very low, but it can be 30% of the radius of the white dwarfs for the lower masses. Okay. There is a paper, I think this the beginning of this year is a postdoc from Pierre-Emmanuel and Boris, that they compute the mass distribution using two different model sets, and you can see the peak in the mass distribution being dependent on that. I don't remember her name. The first author is a girl, and she is a postdoc from Warwick, so you probably know her.
Yeah.
Okay,
yeah.
You can see the effect there. So careful when you go from log G to mass, because it depends what is the mass radius relation they are using.
Yeah, indeed, I'm an observer. So all the models, Pierre is a collaborator.
I'm a modeler. I'm a modeler, so that's why you can see that everything is model related.
Pierre, provide the latest models. I trust you. And that's
Careful, because Pierre-Emmanuel does atmosphere models.
Yeah.
And when you go to radius, is structure models, is interior models. We are two different species.
Yeah, yeah. It's true
when
that
you-
there is the radius mass radius relation is assumed here. Yeah, this is what.
Yeah, but the mass radius relation depends on how much hydrogen is left
Yeah.
on top of the white dwarf.
Yeah, totally right.
Okay, and that changes the mass. You have mass radius. Every log G is dependent on the mass and the radius. If you
Yeah,
have a weird radius, and that uncertainty is also in when you compute the radius from the parallax.
yeah,
Because you also assume a mass radius relation to do that.
yeah, totally agree. Yeah. I have these are the limitations that we have. It's true that also other studies has similar assumptions. So at least for comparing the distributions that we are doing a proper classification, that was the main worry of all the analysis that we did. I think that we're okay given the
No,
limitation.
it's like a lot of people use those models. It's just that so you are aware what you're using, just in case you need to do an interpretation of it.
Yeah,
For
that's the
instance,
thing.
I see that the dB peak in the mass is higher than the dAs, and usually from slow and previous surveys, the dB mass is lower, the peak.
Yeah. Indeed, when we did the analysis with pure helium, this peak was at 0.75 or something like that. So this peak can be whatever you want, just changing things. So yeah, that's true. The thing is that seems to be only one peak. That was the main message from
that's true. That's true. Yes.
the main message. The location, we don't know. Now, as you probably know, meaning that now can be the donor of the electron donor for the atmosphere is not hydrogen, but can be the carbon that is not detectable, but can be dredged from the center. Okay, we will see.
It's a lot of weird things there. Okay, well, thank you. I think that the spectroscopy classification will be very useful because there are a lot of Gaia white dwarfs that we don't really know if they are DAs or DBs. So this data will be very important for us.
Yeah, indeed, there are already some classifications in the market. The thing is that with J-PLUS, is going to be a very good test because we have deeper data with similar resolution, so we can test the selection function and the limitations of the Gaia low resolution spectra. So it's going to be very complemented data sets at the end.
Thank you.
Thank you very much for your comments.
Okay. Do we have questions from the audience? There is one here. In the Kelly comparison, there is an excess of more massive objects. What are those?
Here, it's true that if you go above 1.2, there are some excess. This is because of the volume effect. If you go to these very massive objects, the radius, if you assume a mass radius relation, is going to be very small, so they can only be observed, only the very nearby can be observed, given our selection function. So that means that the volume that we are observing this object is very small. So when you correct with the volume, that is something that I didn't tell you, but there is a volume correction here to take into account all the observational selections that we did in distance, in magnitude, and in parallax. There were an overdensity. We need to wait for future releases to see if this is real or not. But these overdense, these massive objects are real because people make a spectroscopic follow-up of the more massive systems are confirmed that very massive with the spectra. And this is just an observational effect in the sense that we see a couple of them, but if we take into account the selection, we should observe much more. So we will see in the future if this is overdensity is real or is just an observational effect.
Can I answer that question now? That it is real and those are mergers.
Yeah, can be. Yeah.
They are.
Okay. Okay.
That's within the white dwarf community that is known. And there are some population synthesis works that actually predict that overdensity. They are
Okay.
mergers.
Okay, perfect. So I'm happy that that.
Problem solved.
So thank you.
Okay,
May I
is
ask a
there-
question?
Okay, if there is a question, I've not been asking a lot if you want to ask questions, but now go ahead.
I wouldn't
Sorry.
interrupt. My question is on the signal to noise versus magnitude for both the J-PLUS and J-PASS for the telescope and the small telescope.
Yeah. Basically, here we are cutting in 19.5 magnitude. So we have all the analysis that I did provide that we have enough signal to noise to make this comparison. I cannot provide you a proper number, but 19.5 we should be at. I mean, the limiting magnitude in J plus, for example, in the R band is 22, 5 sigma. So we are having high signal to noise. Of course, if you go to the blue bands, always they suffer more. But usually we are at 3, 5 sigma. Of course, we can have objects, but the very cool dwarfs can have very large errors in the red bands, but have really decent errors in the red part of the spectra. So we are confident that the temperature is not very bad. Of course, the classification you can have issues. In the case of J-PLUS, it's deeper, and we make a bigger analysis on that. So we arrive to signal to noise average of more or less, I think that is 20 at 21.5.
Excellent. That's very important because for temperatures below 8,000 degrees, even for DAs, the hydrogen lines are so weak that if you want to distinguish below 8,000 degrees.
Yeah. In the example that I provide is 1,000, and I can check in the paper is the magnitude of this object. This is probably magnitude 19, 19.5, something like that. So this is what we obtain at 19.5 with J-PLUS. So is a couple of magnitudes deeper than J+. So we can go to magnitude 21 or something like that.